2.4 is Applications of Trig Functions. You might notice that section 1.4 also has something to do with applications. So we've got another applications section coming up here. And in this section, what we're going to be taking a look at is using triangles to find quantities that we maybe can't measure directly, which is very similar to what we did in section 1.4. We just have more tools and more abilities in this section than we've had before because we've learned more since then. So our leading idea is the following. Trigonometric functions help us solve problems we can't measure directly by trusting math's patterns. Similarly, faith in God means trusting his plan even when we can't see the full picture. Just as trig reveals hidden answers, faith reveals God's guidance when the way feels unclear. Let's pray. Dear Heavenly Father, I thank you so much for giving us glimpses of how you work in our life through other disciplines, through mathematics, and through the other things that we're working with as we're students. And I pray that you would help our class session today, the details and how this works to all come together in our minds and to be clear. I pray in Jesus' name. Amen. So the basic idea that we're working with in this section, and we will revisit this idea later as well, is that we're going to be solving triangles. So solving a triangle simply means finding all the sides and angles. Okay? Now specifically in this section, we're going to be working with right triangles. Okay? Solving right triangles. We will later work with solving triangles that are not right triangles. So that's why I'm saying we're going to revisit this topic later. So everything in this section is going to be right triangles, just like we've been working with so far. So as we take a look at our first example, you'll notice that they always have to give you 3 pieces of information. Now it looks like there's only 2 here. What's the third piece of information that's not expressly written in, but you do know? The right angle. Okay, does that make sense to everyone? There are 3 pieces of information that you are always given. But for what we're working with in this section, one of them is always going to be a right angle. So our goal is to find all the missing sides and angles. And if we're already given one angle, the third angle is the easiest thing for us to find. Okay, so how can I find this angle here at the top? I'm going to put some letters on my diagram so that we can actually all refer to them as the same thing. We're going to call this point C, okay, the corner where there's the right angle. We always call that one C. And then I'm going to call this one at the top B and the one over here A. There's nothing special about me doing that. I just want us to be able to have a conversation where we're all talking about the same spaces, okay? All right, so this angle B, now that's at the top, how can I find the value, the degree measure for that angle? We are working with degrees. You should smile with that, right? Yes?
So since all 3 angles of a triangle equal 180, first you take out the right angle, which is 90.
Sure.
So then you take 47 degrees out of 90, and that'd be your angle B.
Okay, fantastic. That was exactly correct. So there's a couple of different ways you could sort of set this up. When we move to doing this in general, what we recognize is that the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180, right? That's the general statement for the triangle. But because our angle C is always 90 degrees in these, right? You could always set this up and recognize that the measure of angle A and the measure of angle B is always going to be 90 as well. Okay, so you can start from either of those spaces. It doesn't matter. You'll get the same thing. And just like Cecilia pointed out for us, we've got 47 degrees on the angle A. And you don't have to write all these out. I'm just wanting to make sure everybody sees where it's coming from in case just the talking of it lost you a little bit. We're subtracting our 47, right? So the measure of angle B is going to be what? 43. Okay, so for the most part, you don't need to show any of that probably. Once you get in the hang of doing these, you're just going to look at this and say, hey, look, I'm missing an angle. Those 2 angles add to 90, so I just need to do 90 minus 47. That's going to be my measure of my angle B. So this is one of the 3 pieces of information that we needed to find. And if this is how the problem's set up, it's definitely the easiest of the 3. Okay, it's just a subtraction step right there, okay? All right, we need to find the other 2 sides of the triangle as well. And there's more than one way to do that because you've got 6 trig functions. Some of them are a little easier to use than others, but you do have 6 trig functions. My suggestion to you is to always use something that includes the pieces that were given, just in case you made an error. Let's say you subtracted the 90 minus the 47, and you just totally screwed something up, and instead of getting 43, you got 33. Okay, well, that's an error. But if you only did that piece of it and you didn't use the 33 for any further calculations, it's not going to affect the rest of the problem. Are you with me? So if we just use the pieces that were given to start with, we minimize our chance of making an error because we've already made another error. So we're going to use the 47, and we're going to use that 89.6 that's given on the hypotenuse. And it doesn't really matter which side we find first. This is going to be called side A because it's opposite angle A. And this is side B because it's opposite angle B. Obviously, we've got C over here. Let's find A first, okay? The one that's on the left-hand side. If I want to find side A, okay, and I'm working with the 47 at the bottom and I'm working with the hypotenuse over here, how or what trig function would I use to be able to do that? It's sine. So the sine of the 47 degrees is the opposite, which is A, over the hypotenuse, which is 89.6. That's the trig relationship that exists there. Does that make sense to everyone? Okay. And then what would I have to do to solve for A? Yeah, I'm going to have to move the 89.6 over here, and I do that with multiplication, right? So my side A would be 89.6 sine of 47 degrees. So make sure your calculator, if you've got one that you're using, is in degree mode for this section, right? We've been doing radians on a lot of the other things. Degree mode for this one. What is the 89.6 sine of 47 degrees going to give you?
65.5.
And it says 2 decimal places. I was trying to figure out if it said 2 decimal places. So 65.5, something else after that. 5.3, fantastic. And there are units in the problem. So if there's units in the problem to begin with, like there are here, we're going to make sure our answer has units as well. So it's centimeters. Okay, so technically, if you wanted, could you use the Pythagorean theorem on this? You absolutely could. I'm going to suggest that it might not be the easiest, option number 1, and it might not be the best, option number 2. The reason I say it might not be the easiest option is because we're dealing with decimals and you've got squaring going on, and it's just kind of cumbersome to keep all the decimals sometimes clear and so forth. The reason it might not be the best option is because you're using a value that you found moving forward. So once again, if we made some sort of an error finding the 65.53, we will then carry the error into finding side B. Are you with me? Okay, so will it always end up in an error? Well, of course not. If you want to use the Pythagorean theorem, can you? Of course you can. But I'm going to suggest that there's a better and maybe easier option anyway. So if I wanted to find side B, and I'm only using the side C that I'm given, the 89.6, and the angle that's 47 degrees, what's the trig relationship between those sides? Cosine. That one's cosine. So I can set up a cosine of 47 degrees equals the adjacent, which is B, over the hypotenuse 89.6. And the reason I suggest that this is maybe easier is because it looks just like the last step we did. It's just got cosine in there instead of sine. So it's like I'm just repeating what I already did that I did correctly. So I can move the B, the 89.6 to the other side. So the B is equal to 89.6 cosine of 47 degrees. So what is 89.6 times the cosine of 47 degrees? 61 and 11/100 centimeters. Solving a triangle. I have found 3 pieces of information, right? I was given 3, I found 3, that's all of them. There's 6 things, 3 angles, 3 sides, so we're finished. Okay? What's different about this one? I know it's not drawn in, but can you see just from the information given what's different about this particular one? You're given 2 legs, right? There's no angles given on this one. Y'all with me? Okay, so as we're taking a look at this one, if it helps you, and it will help me, so I'm going to do it, we're going to draw a triangle. If you want to avoid drawing the triangle, I suppose that's your choice. But I'm going to draw it in. So here's my side C. Opposite the side C is the 51 feet. Let me see what I've got written down. I didn't do it this way. That's fine. We'll do A at the bottom and B on the side. So this is side A over here. It's the one I don't know. The B at the bottom is the 32 feet. So these are the pieces of information that I'm given in a visual. I've got 3 pieces. I do have an angle, right? I always am going to have a 90-degree angle in here, and I've got 2 legs. So we need to find 2 angles and a side. Which one do you want to find first? I don't know that there's necessarily an easier option than the other, but there may be a more natural one to you. The side? Okay. So Sydney says she wants to find the side. So if I'm going to find side A, how am I going to do that? Pythagorean theorem, of course. So I've got A squared, that's the one I don't know, plus the B squared is 32 squared, equals the C squared, which is 51 squared. Let's see, I think I have these values written down, so we'll copy them out. 32 squared is 1024, and 51 squared is 2601. Okay, so we'll subtract our 1024. If we do that, we're going to end up with 1577. That kind of looks like a 16. That's better, 1577. And we're going to take a square root, right? So A is going to equal what?
39.71.
Fabulous, 39.71. And my units are feet. So we found one of the 2, or one of the 3, rather, pieces of information we needed. Okay, now I'm not going to use the 39.71 to find any of my angles, right? Okay, it's at the very least we rounded it, and that's going to be potentially problematic later. I definitely rounded this value, and I don't want to use a rounded value in further calculations. Shall we find angle A? So what would I do to find angle A if I'm only using the 2 pieces of information, the 2 sides, that is, of the triangle that I'm given? What trig ratio is going to relate angle A to the 32 and the 51? That's cosine. So I've got the cosine of angle A, which is what I don't know. It's the adjacent, which is 32, over the hypotenuse is just 51. Okay, now we did this back in section 1.4. Like we saw problems like this and knew how to solve them then. Do you remember? What do we do to find angle A in this scenario? We're going to do arc cosine or inverse cosine, exactly. So this angle A will stay here, and the inverse cosine or the arc cosine will move to the other side, right? And remember, what we're really doing here is we're taking the cosine inverse of both sides, and these cancel. And we know that this is going to work because I'm working with an angle measure that's in quadrant 1, actually. That's really what's going on. We talked about that in the last section. All right, so grab your calculator. We're in degree mode. Yay, degrees. What is the inverse cosine of 32 over 51? And it says on the directions to the nearest 10th of a degree.
51.13.
Okay, 10th of a degree is going to mean 1 decimal. 51.1, and it's degrees, right? Degrees. So if you want, you can probably find your other angle based on that. That wasn't a terribly crazy calculation. If you're concerned, based on all of my warnings of fear and dread that I have put in you at this point already, and you want to use another trig function, you could do that. Let me show you both of those options just so that you can make a choice. I don't think it's nearly as problematic when you're working with it in terms of the angles as it is when you're working in terms of rounded sides. But if we're working with this and we're finding angle B, we can actually do that by just taking 90 minus the 51.1. That's one option. If we do that, what are we going to get? 38.9 degrees. So that would be one option. If you're concerned or you just want to check yourself, which is not a bad thing to do either, how would I find, or what would I do to find angle B in terms of trig ratios using the 32 and the 51? Which one relates angle B, that yellow mess that I've kind of marked up there, to 32 and 51? That's sine. So the sine of B is 32 over 51. which means that B would be the inverse sine of 32 over 51. And just check it for good measure. Do we get 38.9? Did it work? Fantastic. So I have 38.9 in either direction that I go. Okay, so typically the way it works is this. Students don't really like application problems with like words in them. That's kind of the way, that's my experience anyway. But I will contend that the application problems with words in them, right, in this section are easier than these problems. What did we have to do to solve a triangle? What was the general idea? We had to find what? All sides and all angles, correct? Okay, so we had to find 3 pieces of information to solve a triangle. When we're working with an actual application, we don't have to find 3 pieces of information. We have to find 1, whatever the problem asks us to find. So here's our example. Suppose that the angle of elevation of the sun is 23.4 degrees. Find the length of the shadow cast by Diane Carr, who is 5 feet 9 inches tall. And it begs for a picture, does it not? Okay, so we've got Diane Carr. This is me drawing a person. It's about as good as it's going to get. I do not draw well. So that's Diane Carr. She has a height. She's 5 feet 9 inches. We're going to have to deal with that in a moment, but we'll deal with that in a moment. She's got a shadow cast. Well, if she's got a shadow cast, it means there's the sun shining down at some sort of an angle on her, right? So I needed a sun drawn up here, so I'm going to draw my sun up here. And the sun is shining down on Diane Carr, and as it does, it casts the shadow, and the shadow is cast on the ground. That's where shadows are, right? Okay, so this isn't like Peter Pan. We're not chasing our shadow. The shadow is on the ground. We can see where it is. That's where we are down there. And it tells us that the shadow is what we're looking for. So we don't know what the length of the shadow is, but it is the unknown quantity. Everybody good so far? All right, do you remember what is meant by angle of elevation? Because we did talk about this, but it's been probably 2.5, 3 weeks. George? Yeah, it is the angle from a horizontal, whatever the horizontal is, up. It's how we're elevating, okay? So this right here is my angle of elevation in the picture. If we were talking about an angle of depression, it's the angle looking down. And in this case, they would actually be the same quantity, but it would be like this piece right here. And some geometric arguments could talk about the fact that those 2 angles are the same thing. But just so you know, if you see that phrase, an angle of elevation and an angle of depression are slightly different in terms of their connotation, but they end up measuring the same space at the same quantity. Let me take that piece off actually so that it doesn't confuse our diagram. So this angle right here is 23.4 degrees. Now we're also assuming, though it doesn't say this, but it's a safe assumption that Diane Carr is not standing sideways, right? Right, she's standing straight up and down, the way you stand all the time for the most part. So this right here is her height, and it is a 90-degree angle. Okay, is everybody good so far? So at this point, we should see a triangle that's being drawn, right? Okay. There's one more piece of information we haven't dealt with, but we are given. What piece of information is that? Her height. It says 5 feet 9 inches tall. That is not 5.9. Right? It's 5. Okay, so how did you get that, Keith?
I took 5 into the long way, but
That's-
converted it to straight inches and then divided that by 12.
Okay, so Keith did it by taking 5 feet and turning 5 feet into inches. So that would be multiplying 5 by 12, adding it to the 9, and then dividing by 12 when you're done. George, you got another way?
Does it have to be in feet?
Does it have to be what?
Does it have to be in feet?
Does it have to be in feet? That's a very good question. So my answer would be that in general, if you're measuring a shadow, you're probably measuring it in feet. But if you had it and you did it into inches, like if you were giving it to me, would I care? And the answer is no. So could you turn it into inches only and leave it that way? What was your inches amount you had, Keith? 69 inches. So if you used 69 inches for her height instead, would that be okay? And the answer would be yes. My math lab might not allow that. And they might also be more specific. And they might say something like, find the length of the shadow in feet. And then you would know. Okay? Let's do it in feet since that's what was mentioned first. I think that may be a little bit more natural in general. But But depending on where the sun is, it could be a very short shadow. I mean, that is possible, but 12 inches or smaller than 12 inches would be very, very short for us to measure it that way. So 5.75, so again, another option that I was going to mention is that we could take our 9 inches and simply divide by 12 to find the decimal point of the feet if we wanted to do it that way too. Either way, you're going to get that her height, in feet anyway, is 5.75 feet. Okay, is everybody good? Now the question is asking about this x at the bottom. So I don't need to find the hypotenuse. I don't need to find the angle at the top, right? It's not what it's asked for. I'm only asked to find the length at the bottom. So the 3 quantities, the 2 that I'm given plus, well, I've given 3, but the 2 that they're not the 90 degrees, the 2 that I'm given, and then the one that I'm trying to find, what trig ratio is going to relate these 3 pieces together?
Tangent.
It's tangent. So this is the tangent of the 23.4 degrees. What's it going to equal? 5.75 over x. Okay, is that okay? So we're going to multiply by x. And if you do this all in one step, you can do that as well, but I'm going to show it out in 2 just for the sake of seeing it this time at least. And then we're going to divide by the tangent of 23.4 degrees. Okay, so if we take 5.75 and we divide this by the tangent of 23.4 degrees, what do we get? We'll do 2 decimals on the length as well, just because that's what we were doing on the previous problems and they weren't giving us any more information on this one, so we'll go ahead and use that. What do you get?
13.29.
13.29 feet. And if you were doing in inches, it would be that number basically times 60. I mean, that's what would end up giving you a very lengthy number of inches, but not incorrect, just a different expression for it.
You say times 60?
I did say times 60, that's not what I meant. Times 12 is what I meant. Thank you for your correction. Start talking too fast. Yes, 60 was what we had for her height, plus her 9 inches. So sorry. Okay, is that good? Okay, let's do one more application. This one says the angle of inclination from the base of the John Hancock Center to the top of the main structure of the Sears Tower is approximately 10.3 degrees. If the main structure of the Sears Tower is 1451 feet tall, how far apart are the 2 skyscrapers? And it says to assume the bases of the 2 buildings are at the same elevation. That's really an important fact that we probably take for granted because we live, and basically, at least at the moment, you live in Oklahoma. Everything's pretty level here, right? If you go to different parts of our country, that's not the case. We went to, 2 summers ago, we were in the Seattle area. Seattle, not on level ground. There's different levels of bases all the time. So this is actually a really important feature. So it tells us that there's 2 skyscrapers. So this is one of my skyscrapers, okay? And then there's one that's next to it, like that. And they're at some sort of distance apart. And that's what I'm looking for. Okay, so it says that the angle of inclination, so inclination means incline. It's the same thing as angle of elevation, okay? The angle of inclination from the base of one building to the height of the other building is a certain measure. You may know that of these 2 buildings that Sears Tower is taller, but even if you don't, it doesn't matter in terms of your picture. If you draw this backwards, it's still going to work. Okay, so the drawing is not going to affect your answers here in a minute. So this base right here is the base that we're referring to, but if you drew it in the other one, you could do that. And it says the angle of inclination, that means as you look upward to the top, essentially, of the other building, so like this length right here, that angle, which is definitely not drawn to scale, is 10.43 degrees. And the angle to that building, then, that building is 1451 feet. So So this is the image that they're describing. And again, if you draw it sort of backwards, where it's the base of the tall building goes to the height of the short building, it doesn't matter. You're still going to get all the same mathematics that we get, okay? It's not going to change anything. So what trig ratio is going to relate the side down here I'm looking for, x, the angle measure I'm given 10.3, and the side that I'm given 1451? Cosine, not quite. It's tangent again. So cosine would relate if I knew the length of this green, because it's the hypotenuse, right? It would have a hypotenuse in it. This 1451 is still just another side of my triangle. So this one's still tangent. Tangent of 10.3 degrees is equal to what in this diagram? It's going to have an x, but there you go. 1451 over x. So we'll multiply the x to the other side, and I'll do it in the same step this time, and we're going to divide by the tangent of the 10.3 degrees. Okay, so these x's cancel. I end up with 1451 divided by tangent 10.3 degrees. What value does that give me? 7,984.34 feet. Did I get that written down right? Yeah. So they're pretty far apart. My picture, definitely not to scale, but it doesn't matter, right? The picture doesn't have to be to scale. It's just giving a picture of where the triangle pieces are. Okay, so there's one more application in this section, and I feel like if I can at least, actually there's two more applications. I think I can get one more of them done, and then the last one will be on a video, okay? So the next application that we're going to take a look at is bearings. So bearings are used in navigation and surveying. The term bearing is used to specify the location of one point relative to another. So we like to work in mathematics in some sense with this idea that there's always this direction picture in our mind, and it's the XY coordinate grid, right? If you're thinking about that picture, north is straight up, south is straight down, east and west have their specific directions, and that works just great. And that's true on our world too, right? We overlay that picture on our world. But if you're trying to consider where, we'll use ships as an example, two ships are in relation to one another, while it matters where they are in relation to the North Pole, that's not really the concern, right? The concern is how they're related to one another. And so that's what bearings do for us. So let me actually show you a couple of pictures of how this works. Let's say we have a point here and we have a point here. I'm going to label this point at the top P and then point bottom O. And I'm going to draw in the sort of distance between them. Actually, let me do it in green too. Okay, so there's a sort of directional space that goes between them if you're trying to go from point O to point P. The way, in fact, let me write that. Oh dear, let's try that again. From O to P. The way that we describe this is we describe it in terms of east, west, north, south kind of directions. So we measure how far that the O is from north. So here's my north direction, right? And we notice that from the straight due north, we would have to go a little bit this direction, right? We'd have to go over here. Let's use this measurement as 40 degrees just so that we have a place to reference it from. Let's say that that is a 40-degree angle. So if this is the picture that's being described, the way that we describe this in language is that we say that it is north 40 degrees west. Okay? If we go straight north and then we go 40 degrees to the west, right? Because I didn't write it in here, but just in case you remember or don't remember, north and south, and then this is west and east, right? We're moving west from the northern direction. That's how we would describe this. Let me draw another picture so that we have another example of this written down. Let's say that again that this is O and P. But this time, notice we'd have to go south. So again, from O to P. This would be south first, right? You'd have to go south. And then this angle measure, let's call it 20 degrees. whatever it is. It's given to you. That's not the problem. I'm not asking you to measure it. But south, and then it's 20 degrees, what? East. This time it went east from that south direction. So we're going to do just a couple of examples of this. These work really quick. That's the good news on these. We're going to draw the bearing described below. It says south 50 degrees west. So I'm going to start with my points here, and I'm going to call it point O, but you can call it whatever, okay? If I go south, it would look like this, right? And if I go west, am I going left or right? I'm going left, and this would be the 50 degrees. Okay, ballpark it, right? 50 degrees, you guys kind of know roughly what that looks like. I'm not asking for a protractor business here. Could be, but I'm not. The next one, here's my O. It says north, so I'm first going to draw in the direction north. And then it says east, which way am I going to go? Going to go right, so it's going to go this way. And not very far, because it actually says 13 degrees. So over here would be north 13 degrees east, and this is the picture that would result. Okay, there's one more application in this section. I'm estimating the video that I'll post is probably 15 or so minutes, give or take. I will be posting a video from last semester, so I'll tell you where to start in that video so that you can make sure and capture the whole piece, okay? But I'll post a separate video for that.